before, which is being recorded, which is great. And I just wanted to say before we get going, there are now open slots on the seminar commission. If some enthusiastic member of the CAB would like to join our team and create some fantastic seminars. So if that is of interest, send me an email and we can chat about it. But I'll hand over to Isaskun to introduce the speaker today. So yeah.
Thank you, Lee. Thank you. I encourage you to join the seminar commission because a very good experience. You know that I was a member for 3 years. You meet a lot of people and it's great for networking. So go for it. Okay, so thank you very much for coming today. So today we have the honor to have Yuri Aikawa, who has flown from Tokyo. And well, I'll introduce the speaker. She did her PhD at the University of Tokyo when she defended her PhD in 1998. Then in 1999, she got a JSPS Research Abroad Fellowship, and then she moved to Ohio State University. She stayed there for a couple of years. And then in early 2000, she moved to University of Tokyo, I guess, no, as a postdoctoral fellow. But then soon after, in May, she moved to Kobe University.
Yeah, Kobe University.
Yeah, to become assistant professor first, then associate professor. And finally, in 2015, she became professor at the University of Tsukuba, where she stayed there for a couple of years. And in 2017, she moved finally to University of Tokyo, which is where she's at the moment, to become professor there. Yuri, so she's a highly distinguished member, astrochemist in the community, and she has won several prizes. She has won the Nishida Prize, and also in 2016 she won the best faculty at the University of Tsukuba, and she works on simulations of the molecular evolution from molecular clouds to protoplanetary disks, and that's what she's going to be talking about today. So Yuri, thank you very much for coming. It's been a very long journey for you, so thanks so much for stopping by Madrid, and the floor is yours.
Yeah, thank you. Yeah, thank you for the introduction. Yeah, I'm working on, well, I started with the modeling person, but the ALMA is so powerful so that my student is also working on some observation of the disks with ALMA. So today I will some combination of the theoretical backgrounds with the observations. And so I mainly talk about the protoplanetary disks where the planets are being formed. And one of the big motivation of this community of planetary system formation that was started like 80s. And at that time, the main goal was to understand how our solar system is formed. But nowadays, with the merge of the many exoplanets, now another aim of our research community is that to understand how those diversity of the exoplanets is formed. Why do we have so many variety of exoplanets like the proto-Jupiters and the super Earth and the Jupiter type, or there are many kinds of exoplanets. So one of the goals is to also understand not only of the origin of our solar system, but also how those diversity will emerge in the planetary system formation. And here I will start with the more classical theoretical hypothesis, which developed in 80s. Yes. Whoops. So, by the way, this is the schematic view of this is artistic image of the protoplanetary disk. The central star is shining at the center, while there is a gaseous that contains also dust in the disk, and that is also maybe we have several forming planets inside, and then there are the dark region is the gap that is covered by the planet. So this is the artistic image, but ALMA is revealing really like this image in a real world And here I will start with more schematic view of the planetary system formation. It's constructed in 70s to 80s. So initially yes, it works. So initially the disk is actually made from the accreting material from the molecular cloud. So the composition of the disk is basically the same as the molecular cloud. So it is 99% of the mass is in the gas, while we have 1% of mass in dust, small solids. And as you know, the planets like Earth is made of rocks. So we have to collect rocks. That's the basics of the planetary system formation. So initially, in the disk, gas and dust are very well mixed, just like in molecular clouds. But initially, the dust grains will first sediment towards the midplane. It's just like if we have a many dust in the room, and initially the dust is flowing with the gas, with the atmosphere. But when the room is very quiet, the dust will eventually settle down to the floor. It's just like that because of the gravity, the dust in the disk will sediment towards the midplane of the disk. That is the first initial step of the planetary formation expected theoretically, physically. And then initially the dust is very small. It's a submicron grain dust. It's the same as the interstellar dust, but we have to make it bigger so they are all rotating around the star many years. So they can sometimes collide with each other. And then if they collide, if you think of a small powder, if they collide, they can stick with each other. And then basically that collisions will make dust to larger pebbles. And then the pebbles will grow to the kilometer-sized rock. That is called planetesimal. It's like a small ingredient of planets. That is theoretically what is expected. And here is the one numerical simulation showing how those pebbles or the grains will grow to larger bodies. So this is the numerical simulation, visualization of the numerical simulation. So this is the local position of the disk. So imagine you are sitting in the boat that is within the disk, and then you are floating in the disk with the rotation of the disk. And then, so this is the animation you will see from the boat. And those small dots are the kind of pebbles or the grains. And then, oops, you see those, well, if you watch carefully, sometimes those pebbles, they are merging, they're colliding. And there's also another one colliding. Oops, it stopped. Yeah, so just like this, though, all the small grains gradually grow to larger bodies by collisions. And eventually, if those pebbles become large enough, they will have its own self-gravity. So the self-gravity also helps to the rocks to become more larger rocks. And that is the expectation from a theoretical point of view. I will skip the details, but well, there is lots of uncertainties, lots of challenges in this, how we can make small dust to large kilometer-sized grains. But since we know planets are there, these events of growing dust should have happened in the solar system as well as in other planet-forming disks. And then once we have these large rocks, they will become a kind of baby planets of the baby Earth, the raw material for the rocky planets. And And well, if we think about the solar system, we also have the gas giants like Jupiter and Saturn. That is made by accreting gaseous material within the disk. So here the brown are the rocky or the dust or the rocks, but this orange shows the gas that is still remaining from the initial stage of the disk. And then, so those orange gases are basically hydrogen, because interstellar medium is mostly made of hydrogen. So there are lots of hydrogen gases still flowing around the star. And those gases are captured by the gravity of the baby Jupiter. And then that planets will become Jovian planets, like the gas giant planets. And if the gas giant planets or the planets become heavy enough, they can interact with the disk, and that can make a gap in the disk because of the gravitational interaction with the growing planets, and the gaseous disks make a gap in the disk. So that's why the artistic image of the planet formation have these kind of gaps in the disk. So yes, and then finally, if you think about the solar system, there is this between the planets. So at the end, the gas in the disk is lost. And then once the gas is lost, that is meaning the completion of the planetary system formation. So this is basically basic scenario for the planetary system formation. So, well, this kind of scenario is made like the basic scenario is already done in late 80s, but now the ALMA is really looking into these systems, and then ALMA can tell us if this scenario is correct or not. The answer is basically it may be correct, but actually, well, there is also significant differences. The conclusion is that such planetary system formation may be happening much earlier than we expected at this era. I mean that yeah. So here is the example of the ALMA images of the protoplanetary disk. This is the ALMA observation. ALMA can observe both a dust continuum, it's a thermal emission of dust, and also can observe molecular lines. So I will start with the dust continuum, which is more easier to understand. It's just a thermal radiation of the small dust grains. So this is the summary of the DSHAF program. This is the first ALMA large program. So ALMA have a large program that is the people make an international big international collaboration team and apply for the large program that can provide us like 100 hours of usage of ALMA. And that will make a kind of very big data, homogeneous data of many disks. And this DSHAP was the first large program in the, well, that was in 2018, is led by Sean Andrews. So this is they observed 20 disks with dust continuum. And as you see, there are many kind of morphologies. And for example, well, basically there are many so-called ring and gap structures. So you see the not only disk, but also the ring and also, well, the gaps between the rings. And then, so this shows also there are diversity of the disk structure. So this is the initial large program. So they only aimed at large disks because small disks are difficult to observe. So they are kind of biased to large disks, but still there are many variety of the morphologies found in the disk. And also there are many gaps. And if you look back into the theoretical expectation, those gaps are expected to form once the very massive planet is formed inside a disk. So when the ALMA was constructed, one of the big aim of the ALMA construction was to look for such gap in the disk that could be a evidence for the planet formation in the disk. And now this large program shows that there are many gaps. So they are, well, although we cannot see in this image planets, but people just very excited that maybe there are already many planets inside the disk. But theoretical astronomer, there was also long discussion if the gap is true evidence for the planets. So according to theoretical work, there are some other mechanisms that can make gaps other than planets. So there are still kind of debate if all those gaps are made by planets or not. But at least from observational point of view, at least some gaps are made by planets. That is evidenced by some observations. And here is one very beautiful example of the forming planets within the disk. This is called the HPDS-70. This is very famous disk. So you see the ring-like structure, and also there is a center. There is also the small disk and the ring. And inside the gap, the European team found a small dots in here. And this dot is not actually a planet itself, but it's a circumplanetary disk. And the lower panel shows the animation of the lower panel is the artistic image, but it explains what I mean by the circumplanetary disk. So there should be a planet like this within the dots. And then if we zoom out to the bigger scale, so there is the disk around the planets. That is what we are seeing in the ALMA image. Yeah, so this is very beautiful animation made by ESO. So this is very clear evidence that actually, at least we found some, there are some systems which actually have planets inside a gap in the disk. And also there is another way of finding planets that is using capillary or the channel map. So if you're familiar with the radio observation, we can also observe the gases in the disk. And because the gas have dust is continuum, so dust emit thermal radiation at a variety of wavelengths, but molecules emit very specific wavelengths. So that can tell us the kinetics, gas motions in the disk using the Doppler shift. So this channel map shows the distribution of the gas velocity within the disk. And so this is each panel shows the gas distribution with a specific velocity. And this pattern shows the rotation of the gas motion. And if you, in some systems, those channel maps are available with very high spatial resolution. And if you, in some disks, there are some weird kinks within those channel maps, which is telling that something is sitting here, although it cannot directly be seen, but there is something in here that is disturbing gas motion. So that tells us something have some gravitational source. So this is the indirect evidence, but it's very robust evidence. Some planets are already sitting here. So this is the one example by Christopher Pante, but there are several systems inside which such planet is already formed. So the conclusion is that we know now that the protoplanetary disk, at least several of them already have the planets inside. So far I talked about the dust continuum as an introductory, but I mainly work on the gas component, molecules in the disk, because I'm astrochemist. And then, so they are also challenge. Well, we are trying to also observe molecules in the disk. So motivation for looking for molecules in the disk is that the main motivation is twofold. First, we want to know about the gas in the disk. So as I said in introduction, the gas should be lost at some point when the planet formation is complete. So we want to know how much gas is left in the system. And also that also tells us the dust gas mass ratio in the disk. And of course, secondly, as an astrochemist, we are interested in learning about the chemical composition in the disk, because those gas and the dust are the raw material, the building blocks of the planetary system. So we want to know the chemical composition of the disks. And so far, this is the summary of the molecules detected within the protoplanetary disks. So including isotopomers, there are more than 50 molecules detected in the disk. And so the first large program, which aimed to look for the molecules in the disk, is the large program called MAPS. That is the molecules in, what was the name? Molecules with ALMA in planet forming scales. That was led by Karion Beck in Harvard, and I was also the co-PI of the project. And then, so this is the disk of one disk. So this is all the images are looking at the same one disk that is called HD 16293. But it's each panel shows different molecules. So we have, this panel shows that the chemical compositions are not homogeneous. It's really inhomogeneous. For example, you can see C2H, that is kind of PDR type species, which is favorably formed once the disk, irradiated by UV radiation, that have kind of ring-like structure. Actually, this ring corresponds to the gap in the dust. So, I skipped the dust continuum image of the system, but there is a, if we look at this object with dust continuum, there is a ring gap structure, and within the dust gap, there is a bright C2H in here. And also, those bunch of the maps shows that chemical composition is very much inhomogeneous within the disk. That actually means that the molecular abundances vary significantly with physical condition, which means that there are chemical evolution continuing within the disk. They are not purely inheriting the molecular cloud chemistry. They are evolving inside the disk. And also it also, for the planet formation, it also tells us that the composition of planets depends on where they are formed. So, it depends on the radial distances from the central star that will determine the chemical composition, and then chemical composition in the disk, but also it determines the chemical composition of the planets from there. And so I'm actually not really I'm more in theory. So radio observer likes these maps, but as a modeler, I prefer the column density distribution. So this is the column density distribution. So this is the object's name, HD 163296. This is the radial distribution. The horizontal axis is the radius from the distance from the central star, and the vertical axis is the column density of each molecule. So there are many molecules detected, so I had to divide it into 4 panels, but they are basically showing column densities. And then within the maps, we have this kind of maps for 5 big disks, and we can learn many things. For example, because we are looking at the molecular lines, we can use line ratio to investigate the temperature distribution. And also the temperature distribution can be derived by looking at the optically thick molecular lines. And also, yeah, this column density tells us the molecular abundances. That is also the vary spatially, that each radius have different molecular compositions. And also, for example, here we have the ions like HCO plus and N2H plus. That is molecular ion because the disk is partially ionized because of the cosmic ray, and also the central star also emits X-ray. So the X-ray can also make those ions. So by looking at detailed analysis of these molecular ions can tell us the ionization degree. And the ionization degree is important in the disk because there are many theoretical studies talking about how the magnetic field will affect the structure and the evolution of the disk. So this is the ionization degree is a very important link to the physics of the disk. And also, well, for the astrochemist, we are interested in, for example, the isotope fractionation. And here we have the N2D plus, N2H plus, that is very high because in the disk, in the midplane, the temperature is very high, where those N2H plus is very abundant. And also DCN versus HCN, that is also, well, tell us the DH ratio. And but maybe the most important result we get from this collection of the molecules is that maybe the elemental abundances are inhomogeneous within the disk. That is very special in the disk. That is pretty much different from molecular cloud. In molecular cloud, elemental abundances should be homogeneous, at least we believe. But in the disk, there is evidences that elemental abundances vary spatially. So here I explain what I mean by the elemental abundance variation and how it is caused, well, the possible mechanisms for the inhomogeneous elemental distribution. So so initially, historically, there is a partial observation of water, the cold water, submillimeter water emission, provided that evidence that the water emission was much weaker than expected. So it tells us that water may be mainly in the ice phase, and then they are settled to the midplane. Also, by the way, this is the intersection of the disk structure. So disk is warmer. Well, disk is heated by the central star. So the temperature is higher in the surface regions, but the midplane is very cold. And also, of course, there is a radial gradient, but also the vertical gradient of the temperature. And the surface is irradiated by UV radiation. And so the surface layer is like a PDR chemistry. It's really like a molecular cloud PDR. But if you go a little bit deeper, there is a layer which is shielded from the UV radiation. So there are a bunch of many molecular molecules, warm molecules are sitting in this orange region, and the midplane is very cold. And then the harsher observation tell us that the water gas is missing, which are telling us that water may be sitting in this blue region. The water is frozen onto the dust grain, and the dust grain can sediment to the midplane, and that is hidden in the midplane. And also the observation also shows that the C2H emission that is very bright in the disk. And if you are a radio observer, you know that C2H is bright in photodissociation region of the molecular cloud. So C2H is it's kind of typical interstellar molecule, but it is rather bright in the disk. And according to the modeling, if we assume usual carbon to oxygen ratio, well, we have still C2H in that case, but the C2H, observed C2H emission is much brighter than expected from the theoretical prediction. And one way to enhance the C2H emission is to change the CO ratio. if the oxygen, well, since the water is the major reservoir of the oxygen, if the water is lost from the gas phase in the warm region due to the ice formation and ice sedimentation to the midplane, this in the warm regions, oxygen is oxygen poor in this region, and that is makes this layer more favorable condition for the hydrocarbon chemistry. So this is the interpretation of the very bright C2H emission in the system. And also there are some sulfur species that are detected in the disk, but the majority of the disks show pretty much abundant CS, but SO is still very limited detection. So the SO versus CO ratio is very low. That is also pointing towards the low, the disk should be very carbon rich, the oxygen poor. And also the there is evidence of the some carbon fractionation in the disk. Somehow the carbon seems to be enriched in 13C. And if you're a astrochemist, you know this carbon isotope fractionation by the exchange reaction. But if the CO, the oxygen is rich, and if the CO is the major reservoir of carbon, you cannot fractionate CO because it is the major reservoir. You cannot change the isotope ratio of major reservoir. But the observation shows that the CO ratio is the carbon isotopic fractionation of CO. That means CO is maybe not the major reservoir. And the explanation is that if we have a high C2O ratio, larger than unity, well, if carbon is more abundant than oxygen, we have extra reserve of carbon that can enable this fractionation of CO, isotope fractionation. And this is the possible mechanisms of this. Well, this is the suggestion from the theoretical point of view. What is happening is that, so this is the zoom up view of this vertical temperature gradient within the disk. So initially the grains are sitting here, and then they are coated by water ice. And as the grains will sediment towards the midplane, the oxygen is lost from the warm regions. And also, we have a very weak turbulence in the disk, and the carbon monoxide will also blow to the cold midplane, which can stick on the ice in the cold region. That makes also the some further depletion of oxygen and some depletion of carbon in this region. And yeah, here is one example of my colleague, the Kenji Furuya, did this numerical simulation. He did the molecular abundance chemical network calculation, including weak turbulence in the disk. And this is the result of his simulation. This is the distance from the central star, and the vertical axis is the elemental abundance in the gas phase. So the inner region is warm, so that in inner region, they can keep a kind of the ISM-like elemental abundances. But in outer regions, because in outer regions, there is a cold midplane that can deplete oxygen in carbon. So the carbon is lost from the gas phase in the outer radius. So the combining with this theoretical expectation and observation tells us that there is a significant elemental fractionation within the disk. So maybe I can skip here. And another interesting topic about the protoplanetary disk is that the maps observation was looking at the so this image is the molecules inside the disks. So we are looking only basically the gas phase chemical species. But since planetary systems are made from solids, we want to know the chemical composition of solids as well. But the observation of solid material chemical composition of solids in the disk is not very easy to observe. But there is a very lucky cases. That is the outburst object. So, so here is the two panels. Here shows in the left-hand side is a usual disk. So the many ices, many solid materials is sitting in the midplane. And since they are in solid phase, we cannot directly observe their chemical composition. And very close to the central star, these ices are sublimated because the inner region is much hotter. But typically, the ice sublimates about 100 Kelvin. And since the disk is very cold, the temperature reaches 100 Kelvin only very close to the star, typically at 1 AU from the central star. And 1 AU is so small, so even ALMA cannot resolve this central region. Nowadays, JWST is looking at this very central region, but the weakness of the JWST is that they can observe only the surface layer of the disk. So we cannot really see the midplane of these warm regions. But there is a special star that is called Yuri outburst system. And currently ALMA is looking at this V8883 Ori. That is the one very popular Yuri star, popular among the astrochemists in the disk. So in this system, the system luminosity is 200 times the solar luminosity. It's really luminous because of the outburst. And then the warm region where the ice can sublimate is actually extended to like maybe 40 AU. And the 40 AU we can resolve with ALMA. And then, yes. And also another lucky point of this object that this is outburst. And typically the outburst phase is only 100 years. And 100 years is short for astrochemists in the astronomical standard. So this is much shorter than the typical gas phase reactions chemical timescale. So if we see lots of molecules in this warm region, we can expect they are fresh sublimates. They are reflecting the ice chemical composition. That is very neat way to investigate the ice composition within the disk. So, so this is the example of the observation image of this lucky star V883 Ori. This is the HDO emission image taken by John Tobin. And astronomers use isotopes of what, well, we of course want to observe water, but there are too much water in the Earth's atmosphere. So radio observer use the isotope of water. So this is the HDO, and the lower panel is the H218O. And using this water observation, John Tobin found that this water in the disk is deuterium rich. So here is the panel of the DH ratio. Well, the vertical axis is the DH ratio, and the horizontal axis is the many object. So so this pink and purple is the cometary DH ratio. And the bar here is the Earth's ocean. And the Earth's ocean is known to be enriched in deuterium. So the interstellar medium DH ratio is 10 to minus 5, but the Earth's ocean is 10 to minus 4. So 10 times high DH ratio is found in Earth's ocean. And this DH ratio is expected to be very important clue for how the water is formed and brought to the Earth. And well, one expectation is that maybe water is coming from the cometary or the asteroid. Water can be brought to the Earth. And this observation of the disk tells us in these disks that deuterium is also rich in water. So maybe enrichment of water in the planetary system may be common among exoplanetary systems because high DH ratio is found in other disks as well. And here is the image of the methanol that is also evaporating around the star. So the sublimation temperature of methanol and water is roughly the same. So if we, in the warm region where the methanol, water is sublimated, we can also find those methanols. Okay, I should skip some events. And also we have many complex organic molecules found in those central warm regions. And this is the analysis done by my student Yoshihide Yamato. And here is the horizontal axis is the bunch of the complex organic molecules, as large molecules, that is organic molecules made of more than 6 atoms. And the vertical axis is their abundances normalized by the methanol. So since methanol is the most abundant complex organic molecules found in molecular clouds and also disks, so we usually normalize the abundance relative to methanol. And those black points shows the molecular abundances found in this V863 Ori outburst object. And here, the blue and orange is the complex organic molecules found in much younger stage. That is called the protostellar core. It's not a disk. It's much earlier stage than the protoplanetary disk. And then if you compare those orange and blue with the black, you can see that the black is high. So which means that disk is have more organic molecules compared with the earlier phase. That will that suggests that maybe the complex organic formation of the complex organic molecules and the chemical evolution is still continuing within the disk. And by the way, this red is the organic molecular abundances found in the Cherifov-Gerasimenko, the Rosetta mission found. Although I put the lower arrow because those are not a spectroscopic observation, they are mass spectrometer, so they cannot really distinguish isomers. So I put my student very careful. So he expected it's a upper limit, but well, it's just because of the different way of detection. So you can see that those red points are kind of very similar. For some species, very similar to the black points, which indicates that we are looking really at the ice composition within the disk that is kind of very similar to the cometary material that is very organic rich. And furthermore, since we have many molecular lines, now we can investigate isotope fractionation in the disk. And this panel shows the carbon isotope fractionation. So vertical axis is the carbon 12C to 13C ratio. And the interstellar medium elemental carbon ratio is about 70 in this region. But this is for example, the Dimitri ether 12C to 13C ratio of the Dimitri ether is much lower. And then, well, my student did analysis of several species, and then they are kind of very close to somewhere between 20 to 30. So it's kind of significant result that tells us that there are really 13C rich complex organic molecules found in the disk. So here is a summary that we are seeing that planets are really forming around the disks, around the young stars. And yeah, well, this is a topic I skipped, but the major revolution brought by ALMA is that, well, classically we expected that planetary formation is happening within the disk of age of million years, that is called class 2 disks. But ALMA found that we already have several planets inside class 2 disks. So the planetary system formation should have started much earlier. That is considered to be called class 01 stage. That is typically 10 to 5 years. And the observation shows that maybe the planet formation rapidly evolves from 10 to 5th year to 10 to 6th year. That is the major revolution brought by ALMA in the physical point of view. And also for astrochemistry point of view, there are many, many molecules are detected in the disk. And we can learn many important factors like ionization and isotope fractionation. But maybe the biggest finding is that we can see the fractionation of elemental abundances within the disk. The chemistry really, not only the molecular abundances, but the elemental abundances have a variation, spatial variation within the disk. That is very important implication for the exoplanet formation. And also, well, finally, we have a lucky star that can tell us about the ice composition in the disk, take advantage of the outburst events that will revealing freshly sublimated gaseous molecules from the ice. And it tells us that ices in those planetary, but the ices in the disk are very organic rich. And well, we are starting to see lots of isotope fractionation within the disk. So that's all I have today. Yeah, thank you for your attention.
Right. Thank you very much, Yuri, for this great talk and exciting talk. Are there any questions here in the room? Yep.
Thank you very much. Very nice seminar. So my question is, what do you think about the ices? Are they formed in the molecular clouds and then they stay up to the protoplanetary disk phase and then you see now in these outbursts what is in the ice? Or it is set up again during the protoplanetary disk formation? Because, for example, the low carbon fractionation, do you think is coming from the cold phases of the molecular cloud or from the cold mid-plane of the disk?
Yes, I think basically it's yeah. So basically I think it's kind of mixture. The basic maybe the inheritance, because if the ices and also gases is falling from the envelope to the disk, and if the dust is covered by ices, and those ices with the ice covered dust will sediment in the midplane very rapidly. In the midplane is very well shielded from the UV radiation or the X-ray. So they are kind of relatively chemically inert. So if this sedimentation happens very rapidly, they have much better chances of the inheritance. But there are still some cooking going on because cosmic rays are still, at least the surface layer is affected by cosmic ray and also the X-ray. So there are a bunch of gas phase reaction is happening here. And also there are some ices still there because there are weak turbulence inside the disk. And in that case, both the gas phase reaction and surface ice mantle chemistry is happening in here. So that can make some extra organic molecules in here. So for example, although I skipped in the FeORI V860ORI, my student also measured the DH ratio of comets. A DH ratio is actually lower compared with the protostellar stage. So they are telling there are some cooking is happening there. So I think it's a mixture of the inheritance and the cooking within the disk.
Yeah. Okay. Is there any other question? Asunción?
Hello, Yuri. Thanks a lot for the talk. About the 12/13 CO ratio, do you find the same for all the molecules or only for the complex organic molecules?
Yeah. So so far the fractionation is found for CO. That is for the tetrahydra. And for this V883 Ori, yeah, the fractionation of complex organic molecules is found in this V883 Ori system. Although I did not bring it here, but there is also the detection that the carbon fractionation is, well, the carbon ratio is measured for HCN, CN, maybe some other, well, there are some other species that people are measured fractionation. And actually there are variation of the ratio. So the conclusion is that they are not really the same as ISM. But the variation among species. So there is now a discussion that how, well, if we can quantitatively explain those ratios. But they are really now starting to see those fractionation in various species.
Because all these molecules are very related to methanol, no? All these ones.
Yes, yeah. So the methanol and the current the comets fractionation is actually yes, those comets are mainly made from CO, and CO goes to methanol, and then methanol
That's
makes
all.
this.
Methanol
that's
form new molecules, and probably you are transferring this.
Yes. So the interpretation of this complex fractionation of complex organic molecules, we expect that is coming from this CO fractionation. Okay. But for other species, we are looking at more surface region of the disk. But basically, they are different from the ISM, and then variation among the molecules. That is really very interesting. Yeah, I should have brought up the latest collection of this fractionation, but I didn't bring it in here. But it's really now a hot topic.
Okay, thank you.
Thank you. Any other question? Yeah. Yeah.
We've got a couple of questions on Zoom, and I'll start with the question from Miriam Garcia, who asks, what is the relevance of the isotope fraction of the organic molecules, and can we relate those findings to what we see on the Earth?
To Earth? Okay. Yeah, I should have brought I think, well, there is a review in the PP7 chapter by Hideko Nomura. She collected all those isotope fractionation measured in the ISM, also in the planetary system. And I did not bring the summary of her review, but I think if I remember correctly, the carbon fractionation is not very clearly detected in the planetary, at least a solar system material. So we are still puzzled how this fractionation found in the disk is connected to the solar system material. Yeah, it's still still kind of mystery for me, at least.
Is there any other question, Lee?
There's one more question on Zoom.
Yeah.
From Pablo Finkel. So he says, thank you for the super interesting talk. You mentioned that the freeze out and dust segmentation can explain spatial isotopic fraction ionization in the disk. But he's not in the field, so he was asking, could you explain a little bit more what you mean by freeze out and dust sedimentation?
Okay. no. Yeah, freeze out is, so freeze out happens not only disk, but in molecular cloud. So basically, well, we have a rocky, well, the mineral grains floating in the interstellar medium, and the dust grains are very cold. If the temperature of the dust grain is as low as 10 Kelvin, many molecules can stick on the grain, and that is called freeze out. For example, in molecular cloud, there are abundant CO molecules, but CO can collide with the grain and stick to the grain as ice. So that freeze out means that the gas phase stick on the grain and make ice. That is a freeze out. And that is observed not only in the disk, but also in a molecular cloud as well. And what is different in molecular cloud and the disk is that in the disk, we have a gravity of the central star that makes the dust grains to fall onto the midplane. Well, this is not the one. In the molecular cloud, there are dust and gases are very well mixed, but within the disk, we have a self-gravity, well, we have a gravity of the star that will drag those dust grains towards the midplane. So this is, go down to the midplane of the disk. That is called the sedimentation of the grains. Yeah, although I skipped, there is another mechanism. If the grains are very little, in the right size, they have a aerodynamical interaction with the gas. Due to the aerodynamic friction, dust grain can also move radially. And typically they are moved towards the center of star, and that will further deplete those oxygen from the outer region of the disk. That will make the change of elemental abundances, both in the vertical direction, but also the radial directions. That is very peculiar about the disk.
Yeah. Okay. And then can I ask one quick question? So it was I think it's very interesting that you see in this disk a lot of oxygen-bearing comets, but you did not mention many nitrogen-bearing comets. So do you have any idea why these disks are nitrogen-poor in comets, in these organics?
Yeah, thanks for bringing out that this V83 Ori is very popular. So there are many groups are pointing towards this object, looking for the many lines. And one of the conclusion is that there is a list. どこだっけ? どれだっけ? どこだっけ? Yeah, sorry. Yes. So this is not the most updated table, but you can see they are mostly oxygen-bearing comets, and only clear detection of the nitrogen-bearing comets is CH3CN. And other than that, there is no nitrogen-bearing comets, which you found very abundant in the central region of the galaxy and also the protostellar cores. So that is very one big mystery or the big challenge in the disk chemistry now, which is becoming clear only recently. And then maybe the one idea is that, that in the comet Cherenkov-Gerasimenko, that they found that lots of ammonia salt. So if the ammonia is become ammonia salt, they cannot make organic molecules. So that may be the one idea, but as I said, that there should be some inherited component from the industrial medium. If the grains are sediment very fast to the midplane, they should keep some fraction of the inherited material from the ISM. So still we do not see not clear detection of nitrogen-bearing comets. So we are still puzzled about this, why the nitrogen-bearing comets are hidden or we cannot detect it. Yeah. But well, luckily that now I know that including large program compass, which I'm not involved, but this object, well, the VH3 is one of the target of the compass. Large program. So we will see if they detect or not.
Nice. Okay. Thank you very much. If there are no other questions, is there one last question?
One more question on Zoom, but I would maybe say so the question's from Miriam Rangel, who maybe can contact the speaker afterwards for some recommendations on planet formation reviews.
Okay.
Which I think would be the best way forward there.
Yeah, I can send the email, definitely. Yes.
Perfect.
Okay, if there are no other questions, then thank you very much for the great seminar, Yuri. And this is the last seminar of the year, no? So we will resume in the new year. So happy holidays and Merry Christmas and Happy New Year.